So in this course, we've spent some time studying polynomials, and we've used derivatives to kind of analyze the graphs of polynomials. In fact, we've used derivatives to help us to determine where the graph of the polynomial is increasing. You can see here it's increasing, moving from left to right. It's going up on this interval here. And also, it's increasing over here. These two places. There you have increasing graphs. And here, you're decreasing. Now, we use the derivative to help us to determine where the function is increasing, where it's decreasing. And the idea is that where the function is increasing, the tangents will have positive slopes. See, look at these positive slopes over here. Here, the tangent's going to have a negative slope. So we say, okay, where the first derivative is positive, the function is increasing. Where it's negative, the function is decreasing. And notice where it all changes. Notice the function is increasing here up to this point, and then it starts to decrease. Now, what we notice is, well, it's at that point right here where the tangent is zero, the slope of the tangent is 0. Now, that corresponds to critical numbers. So, what we want to do, first of all, in determining where this function is increasing and decreasing, we want to find the critical numbers. That's the beginning. Okay? So, here we go. We find the derivative. And in this case, it's going to be x squared minus x minus 12. Just using the power rule. I just differentiated this function. Okay? Using the power rule, remember, the power rule goes a little something like this. Yeah, like that. Now, what I do then is, okay, so this is the derivative, and remember, this is a machine. You put in an x and it spits out slopes of tangents. Well, I want to know what do I put in here? What value of x do I put in here so that it spits out a 0? In other words, so I get a tangent of 0. So I'm going to solve this. I'm going to take this x squared minus x minus 12, set that equal to 0. So here I go. I'm going to solve this by factoring. You solve it any way you can. This one will factor, so I'll solve by factoring. We could have used the quadratic formula here, but I factor this. So I need numbers that multiply to give me negative 12, and add to give me negative 1. I think negative 4 and plus 3. Yeah, that works. So we got that x equals negative 3 or x equals 4. That's where you have a derivative of 0. If you put in a negative 3 in here, that's 0. If you put in a 4 in here, that's 0. So there are two critical numbers. And you notice on the graph, look at this. Here's a negative 3, and here is a 4 down here. Okay? So those are our critical numbers. Now, what do we do with those? Well, I make a little number line, and I put a negative 3 here and a 4 here. And I want to see where the derivative is positive, where the derivative is negative. So I'm going to use these critical numbers where the derivative is 0 to divide the number line. So I'll pick test numbers. Anything less than negative 3, I'll pick negative 4. Anything between negative 3 and 4, 0 is a good one. Anything bigger than 4, I'll pick a 5. Okay? Now I test these values. So I've got x. I'm going to test the values here. And I've got my function, not the original function, but the derivative, because I'm interested in seeing where that derivative is positive, where it's negative. And I'm going to test negative 4, 0, and 5. So if I put in a negative 4, this first factor here is obviously going to be negative. And the second one, it's a negative as well. A negative times a negative is a positive. So that tells me that in this interval, our function is increasing. Now let's put in a 0. Well, if I put in a 0, 0 plus 3, that's positive. 0 minus 4, that's negative. So that's negative. So this is decreasing here. And then let's try the 5. We get a positive times a positive is a positive, so this is increasing. So the function is increasing from negative infinity to negative 3. And it's also increasing from 4 to infinity. So if you give me an x in either one of those regions, either from negative infinity to negative 3 or from 4 to infinity, that's where it's increasing. Now, where it's decreasing, well, the other place, negative 3 to 4. Okay? Now, that's what we can do with that first derivative. It's very powerful. Now, let's look at concavity. In other words, the function, notice that the function is increasing here. It's decreasing over here. But notice that here, the function is concave down. And at some point here, it transitions over to concave up. In other words, it's opening up over here. That's concave up. This is concave down, where there's a transition. Now remember, the way we find that transition, that inflection point, is with the second derivative. And when the second derivative is positive, remember it's concave up. When the second derivative is negative, it's concave down. And when you go from concave up to down, or vice versa, that point where that change happens is the inflection point. So let's find the second derivative. So we've got x squared minus x minus 12. So the second derivative is 2x minus 1. There's the second derivative right there. See? So I'm just differentiating this derivative. X squared minus x minus 12. Okay? There that is. Now, I set that equal to 0. And I get that x equals 1/2. Now, I just repeat what I just did for the first derivative. I make a number line, locate 1/2 on that number line, pick a test value to the left, maybe 0, test value to the right, 1, and then I plug that in. Okay, so I plug in my test value, 0, 1, and this is going to be 2x minus 1. Well, this is going to be negative when I put in a 0, so that's concave down. When I put in a 1, I get a positive, so that's concave up. So it's concave down from negative infinity to 1/2. It's concave up from 1/2 to infinity. And the inflection is at x equals 1/2. That's where it occurs. So the inflection point would be 1/2. The inflection point would be 1/2 comma f of 1/2. That's actually the inflection point. But the inflection occurs whenever x equals 1. Now, the other thing we did with the derivative is we found equations for the equation for the tangent and the equation for the normal. So let's do that next. Here's what we've got here. We've got the graph, and what I've done here is I've labeled the green here, that's the tangent, at x equals 1. So there's the tangent, and over here is the normal, the perpendicular to that tangent. Now, remember how we find the slope of the tangent. It's the derivative. So what we want to do is we want to say, okay, I want the derivative f prime of 1. So that's going to be 1 squared minus 1 minus 12. So it looks like that's negative 12. That right there is our slope of the tangent. So this is m. I'll call that the slope of tangent. Likewise, 1 over 12, the reciprocal, the negative reciprocal, equals the slope of the normal. So we've got our slope of tangent, which is negative 12, slope of the normal, which is 1/12. So now here's what we do. We go y equals, okay, negative 12. This is the tangent. Okay, y equals negative 12 times x minus 1 plus f of 1. I've got to find out what f of 1 is. And the normal would be 1/12 x minus 1 plus f of 1. Very similar. So there's the normal and there's the tangent. Now, we get the normal, or we get the f of 1 just by plugging back in to the original function. So f of 1. So that's how we would get that f of 1. And you can do that computation yourself. I don't want to take up the video time, but you would just put a 1 in for x on the original function. And that's where you would get that point. And it's going to be negative 11.167. You can see that here.